Backbed reactor is a type of tubular reactor where reactants flow through the reactor through packing without radial variation in reaction rate. It operates at steady state and is normally assumed to be perfectly mixed without dependence to any variables in the reactor. In cases where non-ideal mixing and unsteady state behavior investigated, residence time distribution is used to characterize the flow of reactants in the reactor. It can be operated in co-current or counter-current modes, where the former is most common in the oil and gas industry with the aid of catalysts. The PBR reactor used in our experiment was operated in bubble mode, in both co-current and counter-current modes. These operation modes are most suitable when liquid reactants are treated with small amount of gas. The residence time distribution of a reactor is a characteristic of the mixing that occurs in the chemical reactor. The residence time distribution is determined experimentally by injecting an inert chemical molecule or atom called a tracer into the reactor at some time t equal to 0, and then measuring the tracer concentration C in the effluent stream as a function of time. The tracer should have physical properties similar to those of the reacting mixture and be completely soluble in the mixture. It is also should not absorb on the wall or other surfaces in the reactor. The later requirements are needed so that tracer's behavior will reflect that of the material flowing through reactor. The different input utilized in this experiment will produce different system responses, as displayed by the graph. The main objective of this experiment is to determine the effect of liquid and gas feed rates on the mean residence time and degree of liquid phase axial dispersion. The effects of step change and fast inputs are studied in experiments A and B respectively. In this experiment, the effects of step change input and fast input are examined. The operation modes for both inputs are countercurrent and co-current mode. In countercurrent mode, the liquid stream is flowing downward from top of the column,
while the gas stream is flowing upward from bottom of the column. The pulse or step input tracer is injected at the top of the column. In co-current mode, both the liquid and gas streams are flowing upward from bottom of the column. The pulse or step input tracer is injected at the bottom of the column. For the operation of the system, an input is introduced and conductivity measurements is used as a parameter to monitor progression of tracer. The data and readings can be observed from the screen of the computer by using the appropriate software.
These are the data obtained from operating the equipment in counter-current mode with step change input. Mean residence time, spread of distribution, and skewness are calculated from experimental data and will be explained in the discussion section. This figure shows the graph of residence time distribution versus time for counter-current step change input. These are the data obtained from operating the equipment in co-current mode with step change input. And this figure shows the graph of residence time distribution versus time for co-current step change input. These are the data obtained from operating the equipment in counter-current mode with pulse input. The figure shows the graph of residence time distribution versus time for counter-current pulse input. These are the data obtained from operating the equipment in co-current mode with pulse input. The figure shows the graph of residence time distribution versus time for co-current pulse input. The concentration of the tracer at the outlet is calculated using the formula shown. This formula is obtained from the concentration versus conductivity calibration curve with the assumption that the graph is linear and begins from zero to prevent negative values of concentration. Next, residence time distribution is calculated for step change input. Residence time calculations for co-current and counter-current operations are the same. Our residence time distribution is defined by the differential of tracer concentration at the outlet over a small period of time. On the other hand, residence time distribution for pulse input is characterized by the expression of output tracer concentration over the integral of the concentration. Mean residence time, variance, and skewness calculations are the same for both step change and pulse input, regardless of co-current or counter-current operation modes. Mean residence time is characterized by the integral of the product of time and residence time distribution over the period of time investigated. Variance is calculated by integrating the product of the square of the difference between time and mean residence time with residence time distribution. The skewness is calculated by using the formula shown by relating the standard deviation, difference between time and mean residence time and residence time distribution. Dispersion characterizes the spreading of the tracer across the reactor. Large dispersion values mean rapid spreading of tracer and vice versa for low dispersion values. Dispersion is calculated by dividing variance with the square of residence time. If the vessel dispersion numbers are more than 0.01, it means that the system has large dispersion. If the vessel dispersion numbers are lesser than 0.01, thus it means that the system has smaller dispersion.
Similar trends can be seen for pulse input and step change inputs respectively, regardless of co-current or counter-current flow setup. These trends are similar in terms of shape of the graph as their respective concentration curves. However, it can be seen from the graph that components spend more time in the reactor operating in co-current setup compared to counter-current setup, which also implies that reactants will take a longer time to leave the reactor. Comparing both figure 2 and 3, a large portion of the reactants stay for a longer period of time in co-current operation than in counter-current operation. Having said that, reactions in co-current flow would be able to achieve higher conversion rates than in counter-current flow. It is therefore assumed that non-ideal mixing occur in the reactor. The mean residence time Tm for both pulse input and step change input are shorter in counter-current operation than co-current operation, which justifies the deductions and observations made earlier. Similarly, the standard deviations for co-current operations for both step change and pulse input are higher than counter-current operations. This means that the distribution in co-current operation is more spread out, which supports the implication made earlier that suggests that co-current operation might allow higher conversion of reactants in the reactor. Last but not least, the skewness of all the operation modes for both step input and pulse input are positive, meaning that the mass of the distributions are concentrated to the right. This can be seen in all the graphs in the figures shown previously, where there are right tails for pulse input as well as the bulk of the RTD concentrated on the right side of the graph in step input.
Based on the results obtained for the dispersion system in experiment A, the vessel dispersion number d over pi L for step change input countercurrent is 0.032, which is more than 0.01. Thus, the system has large dispersion. Whereas for step change input co-current, the vessel dispersion number is about 0.0091, which is lesser than 0.01, thus giving the system a small dispersion. From the comparison above, it can be seen that the vessel dispersion number in countercurrent mode for step input is larger than co-current mode. This means that the system in countercurrent step change has larger dispersion coefficient, which gives rapid spreading of the tracer curve. In experiment B, the vessel dispersion number for pulse input countercurrent is 0.094, which is more than 0.01. Thus, the system has large dispersion. For pulse input, the vessel dispersion number is 0.128, which gives more than 0.01 and larger dispersion. In comparison of the dispersion coefficient in countercurrent and co-current, the coefficient in co-current can be seen slightly higher than in countercurrent. This might be due to slight deviation or disturbance in the countercurrent flow. For experiment A, the mean residence time for co-current flow is higher than in countercurrent flow. Thus, it can be said that the resistance for a tracer to flow in the reactor column is lower for countercurrent flow. For experiment B, the mean residence time for co-current flow is higher than in countercurrent flow. Dispersion in co-current is higher than in countercurrent for both pulse and step change input.